Hello everyone, welcome again to another one of Mr. Martin's math videos. This is a video specifically for Pre-Calculus 12. We're looking at Chapter 8, Section 2, Transformations of Logarithms. So again, we find ourselves analyzing different ways that a function can be transformed. So throwback, and it's due on Thursday, so I guess a bit of a throwback Thursday. To our first chapter that we did in this course, right? And something that we've done for every single function we looked at in this course, so far, is these transformations. So this section basically follows the same structure as before. Know what the different parameters of the transformation do and how to apply them to our base equation. So the general form for transformations of logarithmic function look like this: y is equal to a. So we know what a is, right? A does vertical stretch, b by a factor of a. B does horizontal stretch by a factor of 1 over b. H does horizontal translation, and k does vertical translation. All right, so those are our 4 parameters there. All right, the process of transforming functions should be second nature by now. Let's just review an example so that we're all on the same page. So again, here, a big part to remember here is also the mapping notation. What happens to the mapping notation, the x and y values of a point after they've been transformed? So if you guys remember, it's 1 over bx plus h and ay plus k. Okay, so that's what we're going to be using here to determine the new points on the graph and to be able to graph this new equation here. So here they have a function y is equal to log 2x, and these are the points that they give us based on this function. Okay, so these are going to be in green, and I'm just going to plot these and graph the line. So I have 1 and 0, which is here. I have 2 and 1, which is here. I have 4 and 2, which is here. And I have 8 and 3, which is here. Okay? And so I can kind of see my line coming from negative infinity in the y direction and then doing this curve like that. Okay? So that would be our basic log function. And then this function gets transformed. So I want to determine what are the transformations here. So a, b, h, and k, because that will help me then determine my mapping notation that I'm going to need to use to graph this transformed function. So the a value here, all right, is that negative there, negative 1. Okay, so that's negative 1. The b value is 2. All right, this is where it gets a little bit tricky here. H value, I don't have a k value, so the k value I can write in right away is 0. There is no k value. But the h value, remember that the b needs to be factored out with from the x minus h to solve for your h value here. So here you actually need to factor this little expression here into 2 bracket x plus 3 bracket bracket. And then we can determine our h value as being negative 3, okay, because it's x minus h, so this would give me negative 3. All right, so hopefully you guys were able to follow that and remember that from chapter 1 and the other chapters that we've done this. So now that we have a, b, h, and k value, we can determine our mapping notation, right? And so for this situation here, we have our x and y values that we're starting off with our regular untransformed log function. And then this is going to turn into, and again, I'm looking at the top right corner there, that green highlight, 1 over b. So we determine that b is 2. So it's 1 over 2. 1 over 2 x plus h. In this case, h is minus 3. So minus 3. and then a is negative 1 y plus k, in this case plus 0, so we don't have to put anything. And that would be our mapping notation based on this transformation. All right, now we just have to do these operations to each of the numbers, and we get our points that we're going to graph. All right, so for 0, or for the 1, so 1 times a half is 0.5, minus 3 is negative 2.5, and 0 times negative 1 is still 0. All right, 2 times a half is 1, minus 3 is negative 2, and 1 times negative 1 is negative 1. 4 times a half is 2, minus 3 is negative 1, and 2 times negative 1 is negative 2. And 8 times a half is 4, minus 3 is positive 1, and 3 times negative 1 is negative 3. So these are my new points. We didn't really have to move it over 3. If you just have the proper mapping notation right off the bat using this kind of key, then we can move right to our points and then graph our new line. Okay, so I'm going to graph this line in red. So where are these points? Negative 5 and negative 2.5 and 0 is this point here. Negative 2 and negative 1 is this point here. Negative 1, negative 2 is this point here, and 1 and negative 3 is this point here. Okay, so you'll notice that there's been a compression of my points. If you compare this like this to, and here it would be something like this, and then curving, and then kind of out like that. Okay. If you were, and so if I'm comparing right now the width, right, and so here this is a width between those 4 points. I have 1, 2, 3, 4, 5, 6, 7 blocks, okay, 7 units, where here I have 1, 2, 3.5. So I can see that I've gone from 7 of my 4 points. I had a domain of 7, and I've gone to a domain of 3.5 here, which you would expect with a b value of 2, right? A horizontal stretch of 1 over b, or 1/2. Okay? A y value, okay, notice here that they're the same in magnitude, but they're going upwards, right? Up 3 kind of blocks, but these ones are 3 units. These ones are going downwards, but still 3 units. And so that is indicative of that negative a value, okay? And we also have a reflection off the x-axis, okay? And that's being shown there. And then we have a translation negative 3. So they've moved negative 3 to the left, okay? And that's specifically kind of demonstrated here where the asymptote is. And so here the asymptote of our original function was the 0 line. Okay, for this function, it's the negative 3 line. That's the new asymptote. Okay, so that is that negative 3 h value. Okay, that's where it shows up here, is the movement of the asymptote. All right, so hopefully you guys are able to track that, see that. Hopefully this is familiar territory for us because we've done this before. So let's answer some of these questions here, based on the graph above, specifically the red line. So identify each of the following characteristics of the graph of the transform function. The equation of the s of any asymptote. So here we're just looking at the transform function. So the equation of the asymptote is x is equal to negative 3. Domain and range. Well, my domain is x is greater than 3, greater than negative 3, and of course x represents all real numbers, and my range y is just all real numbers. Okay. X and y intercept. Okay, x-intercept we know is negative 2.5. Okay, because that happens at negative 2.5 and 0, which is one of the points that we got when we transform. For the y-intercept here, I need to plug in an x value into my equation to make it equal 0. So if I take my equation of y is equal to log base 2, and then 2, and then here I substitute 0 plus 6, what is y equal to? Okay, and whatever y is equal to, that's my y-intercept. So I'm just plugging in the x value into my equation. Oh, sorry, this is negative log 2. All right, so I plug this into my calculator. Negative math log base 2 to the 2 times 0 is 0, it's 2 to the 6. And I get negative 2.58. Negative 2.58. So the point of my y-intercept would be 0, negative 2.58. Okay? So those would be your solutions there for the x and y intercept. All right, so now, of course, we have to know not just how to go from a transformed equation to a transformed graph, but determining a transformed equation from a transformed graph. Okay, we're working backwards. So the thick line graph shown below can be created by transforming the skinny line graph and then find the equation of the thick line graph. The skinny line graph has an equation of y is equal to log base 4x. Okay, so in this situation here, we have to determine what values were affected, first of all, by the by this transformation here. Okay, so again, and it's A, B, H, and K. So A, was there any change vertically for A to determine? So our A value, we're going from A to A prime here. It hasn't gone up, and it hasn't been stretched. The graph hasn't been stretched. It looks like it's the same shape of graph. It's just moved. It's just moved up. However, the A point has not moved up. It's actually moved over to the left. And so here, our A value and H value are irrelevant. Okay? Or K value, sorry, my mistake. A and K value are irrelevant. Now we can look at the B and H. Now the H, we saw that the H value here moved the asymptote over. Okay, did the asymptote of the thick line change compared to the thin line? And the answer is no. So the H is irrelevant. So here we're only looking for what happened to the B value here. Okay, so here we're looking at, if you compare it to the asymptote, it's going from 4 units here to just 1 unit here. Okay, so it's been compressed, or it's been stretched by a factor of 1 over 4, right? If you were to describe it, it's had a horizontal stretch by a factor of 1 over 4, because you multiplied by a quarter, right? And so that makes my B value equal to 4. So if I were to find the transformed graph here, it would be y is equal to log base 4 and then bracket 4x. Hang on, let me not put in bracket and then x, close bracket, and I'm going to put my 4 in red. So you see what exactly was the transformation, the difference between the original graph that we have and our final answer. Okay? So we were able to cancel out the A, the H, and the K, and we saw that was just the B at work here. Okay? Other questions won't even give us a graph. They'll just give us points. Okay, which might seem even more intimidating, and in some ways these are definitely harder questions. I want you guys to, you guys have the skills to solve this, so I want you guys to pause the video and try this on your own. If you want, you can sketch a graph, the original graph and the transformed version of the graph. Look at what the points without the transformation would be versus with the transformation, and see if you can determine exactly. And here they do limit it, right? They're looking for an A and K value. Okay, there's no B and H value here. It's just A and K. So that should help you and reduce your options for this graph. So go ahead and pause and try to get as far as you can in this question, and we'll come back and do it together. All right, hopefully that went well for you. Let's take a look. So the first thing we got to figure out, okay, what outputs does this graph normally give us? Okay, because here, this are transformed points. So we got to figure out, okay, what were the original points? Okay, so if I say f of x is equal to log 3, okay, and I want to know, okay, what does log 3 and an input of 3 normally give me? Okay, and this would give me an output of 1, right? So the original point was 3 and 1, but the transform point became 3 and negative 2. Okay, so we get an idea of the transformation here. The 3 didn't change because we know that the B and the H value aren't affected here. In terms of, there's no transformation caused by a B or H value. It's only transformation caused by A and K values. Same thing with the other point. F of x is equal to log 3 and then to the 9. Okay, and again, these are pretty simple here. This would equal 2. All right, so here I have 9 and 2 was the untransformed point. So if this was A, then this would be A prime, right? And this is B, and then we know that B prime turned into 9 and negative 9. That's B untransformed, and then B prime is the transformed. So this gives us a bit of a starting point, and you could actually figure out what the A and K value is by kind of trial and error and plugging in various values for A and K just with these 2 points. However, there's a more kind of sure algebraic way that we can go about this as well. So this is a good starting point there. Shows us transformation, and it will be a good place for us to be able to test our findings later on to see if they actually work for both of these points here. Okay. Another good thing to do is to kind of sketch a graph. Never a bad thing to do here to determine, the original graph, and then additional points from there, right? And so we know the x-intercept is 1. We know the point of 3 and 1 and 9 and 2, right? So let's say if this is 3, this is 6, and this is 9, and this is 2 and 1. This is 1 and 2. And so your original graph kind of, let me just write a couple numbers here, 3, 9, 1. Okay, the original graph kind of looked like this. Okay? And then the transformed graph, it looks like this. We have 3 and negative 2, which is this point here. 3 and negative 2. And we also have 9 and negative 9, which, I gotta drop this x-axis or y-axis lower here. 9 and let's say negative 4. Negative 8 would be here, so let's say negative 9 is here. Negative 9. So this just gives me a graph to give me an idea of what the graph would look like here, eyeballing it. So we got, some kind of line that's going to be going through these points here. Okay. However, it doesn't give us that much information. It's not that helpful, but it does kind of show us, okay, there's obviously a reflection here. So I'm going to have, my A value is going to have a negative. That I can see clearly from my graph, something I might not have been able to see clearly from the points. So A value is going to be negative. That's a guarantee. Okay? But otherwise, it doesn't give us a whole lot to go off of. Okay? Now, one of the best ways to go about this is to actually create a systems of equations, okay, because you have the 2 points that you have here. So, again, you have our first equation. Let's say we were to input, and we have the input and outputs, right? So if I had A is equal to, oh no, it's not A, sorry, f of x. Original equation here is g of x is equal to A log 3x plus k. Okay, now we have values for g, x, and x, right? We have input and output values for our transform function here and here. That just leaves me with 2 variables that are not solved. And whenever you have a problem that has 2 variables that you're solving for, your mind should automatically now go to, oh, systems of equations. That's how I'm going to get through this, okay? And that's what we're going to try here, all right? So I'm going to replace g of x with -9. I'm going to use b prime first. You could use the other one. It doesn't matter which one you do first. And then times a log 3 to the 9 plus k. Okay, so I have that. And then I'm going to try to simplify. Okay, first thing I can simplify here is 9 is equal to a, and log 3 to the 9 just by itself is equal to 2, right? And then plus k. So here, -9 is equal to 2a plus k, and I want to isolate one of my variables. I'm going to isolate my a variable. Okay, so I'm going to bring the k over to the other side, so minus k, and then, divided by 2. I'll just do one step at a time here. That's going to give me -9 minus k is equal to 2a. Divided by 2, a is equal to -9 minus k over 2. Okay, so that's what one of my variables is equal to. Then you do the same thing with the other variable. Or what you can do actually is just plug this in to the a value in the other equation. So if I have now my other equation, same starting equation, but now instead of using b prime, I'm going to use a prime, plug those values in, okay? I'm going to have -2 is equal to, now instead of putting a, I'm going to substitute what a is equal to, -9 minus k over 2. And then, I put in log 3, and then my input to get an output of -2 was positive 3, and then plus k. Now this looks complicated, but it simplifies actually pretty quickly and pretty nicely here, because log 3 to the 3, this equals 1. I know that because we did that up here, right? Equals 1. And so I can substitute that log 3 to the 3 out right away with a 1, okay, which gives me -2 is equal to -9 minus k over 2 times 1, which is just as is, so there's no real need for a bracket here, times 1, which just is, and then plus k. Okay, and then you just go to work algebraically here, flatten out your equation, and then get your variables on the same side. So if I do minus k, I get -2 minus k. This is equal to -9 minus k over 2. Then I'm going to multiply both sides by 2. That's going to cancel out the 2 here, and I get -4 minus 2k is equal to -9 minus k. Okay, and then we go from there. So let's bring this 2k plus 2k plus 9, and that gives me k is equal to 5. So there's my value for k. I know that k is equal to 5, okay? And then at this point, I can plug in my k value into the equation I ended up with here to get my a value, right? And so let's do that off on the black area here. So negative 9 minus k over 2 is equal to a. Negative 9. Substitute what I know k is equal to there. Over 2 is equal to a. So negative 9 minus 5 is negative 14 divided by 2 is negative 7 is equal to a. And we expected a negative value, right? Based on our graph, we expected there to be a vertical reflection. And then that would be our solution right there. So systems of equations to the rescue once again. All right, make sure you know how to do those. That's the notes for today. This is your homework right here, due Thursday. If you have any questions, drop them in the comments or in the homework question channel in Teams app if you're in my class. And hope this video was helpful for you. We'll see you next time. Goodbye.